I'm asked to talk about limits. Let me move this. So let's read those notes first. A function f is continuous as x equals a, provided the graph does not have any holes, jumps, or breaks at x equals a. So what does it mean? It means there's a solid dot there. So the whole graph is just one piece of string. There's no break, no hole, or no jump. So when function is continuous, then we can have this relationship. The function value, so the function evaluate at a equals to the limit when x approaches to a of the function value f of x. Right, so those two equals to each other. I assume you know the definition of limits, right? So this notation means the left limit and the right limit agree with each other. Right, so usually we use a rather in the exponent place, like a plus. Maybe let me write this. It's a little bit difficult for me to write the limit x approaches to a from the right. We do a little bit plus, a little plus here. Then f of x. So similarly, so this is called the right limit at x equals 8. And if this equals to the left limit, we use x approaches to a with a minus in the exponent place. Okay, this is the function f. So when those two agree with each other, imagine a graph. So let's say this is a point 8. So the x value is 8. And the graph comes from the left-hand side, reaches this value. And the graph comes from the right-hand side, also reaches this value. So that's, so you see it connects the two pieces of strings to be one piece. So this means the function is continuous, or it's just, visualize that. And when this limit exists, that means the left limit and the right limit to the same place. Sometimes it may not equal to the function value if that's a hole, right? If there's an empty hole, that means a is not in the domain of the function. If it is not in the domain of the function, we won't have f of a. But for continuous function, you can imagine as one piece of string, right? It may have some jumps, but it's just one piece. A couple functions have these kind of features. Polynomial function family. Trying to bring up my pencil. So polynomial families, this is a degree 3, or for any degree of the polynomial functions, constant functions, linear functions, quadratic functions, cubic functions, quadratic, quintic, so on and so forth, polynomial degree n. So their domain is all real numbers. So if the domain is all real numbers, the function is continuous. The function works for all real numbers. So function is continuous on all real numbers. Then the limit just equals to the function value. So rational functions is a kind of tricky because we have to consider the denominator not to be 0 for domain. Right? For domain. In this case, we see this one can be factored. The denominator can be factored as x minus 3, x plus 2. Then when this equals to 0, we say x equals to 3, x equals to -2. That creates two asymptotes. That means the 3 and -2 is not in the domain of this rational function. That means the function is not continuous at x equals to 3 and at x equals to -2. So then we can talk about the limit from the left-hand side of 3, from the right-hand side of 3, from the left-hand side of -2, from the right-hand side of -2. Radical functions. Radical functions, we have to consider the inside non-negative, right? So 2x minus 5 has to be greater than or equal to 0, which means at least 0. In this case, that means x is at least 5/2. So if the value, think about the limit of x approaches to a value. If the value is in the domain of the function, it just equals to its function value. The next one is exponential functions, right? For exponential functions, we know the domain is also all real numbers. So that means the limit at any point of the real number, this function, the limit of this function at any point equals to the function value. Or log functions, the domain is inside this value has to be greater than 0. So in this case, 3x minus 8 has to be greater than 0, which means x has to be greater than a divided by 3. So in the domain of this function, for every value, the limit for every value of x, the limit of f equals to the function value. All right. So let's see some examples. So this is a polynomial function. So quadratic function, right? We know any polynomial function or quadratic function. This is a quadratic function. It's a polynomial degree 2 function. So it just equals to the limit when x approaches 3, just equals f of 3. We just evaluate the function. So that's a 3 squared plus 4 times 3 plus 1, which give us 9 plus 12 plus 1, which equals to 22, right? Because 9 plus 1 is 10, 10 plus 12 is 22. So if a function is continuous at the point, for this one now, the point is 3, right? If the function is, if this number is in the domain of this function, so it just equals to its function value. So we just evaluate at the number. So that's the easy part. Oh, actually the work is done here, right? Let's say second example. Second example, we have limit x approaches to 1, x squared minus 1 divided by x minus 1. Well, x squared minus 1 is the difference of two squares. Difference of two squares can be read in two factors, right? X minus 1, x plus 1. Then the factor in the numerator, x minus 1, simplify the factor in the denominator, x minus 1. So then the function becomes just x plus 1. Now 1 is in the domain. So in the beginning, 1 is not in the domain, right? Because if we do 1 minus 1, we get a 0 in the denominator. Well, 0 cannot be in the denominator in our math, in mathematics. But now somehow after this consolation, 1 is in the domain of this new simplified function. Oh, which is one is in the domain of this function, we just evaluate, right? Just plug 1 for x, that 1 plus 1, that's 2. So what about the graph? The graph x plus 1 is a linear function. If we draw the line x plus 1, it's just this line, right? Just this line. But this in the beginning is a rational function. In the beginning, it says 1 is not in the domain. So we make an open circle above 1. So because this 1 is not in the domain of the original function. So we won't be able to talk about f of 1. F of 1 does not exist. So we indicate with an open circle. Now you see this open circle splits this line into 2 pieces, right? So one piece, this is one piece, and this is another piece. So we see this is a hole here. There's a hole here. So this is one type of rational functions can be simplified. Well, let's see this one. So the numerator will have x plus 2 divided by x minus 2. The denominator will have x minus 2. And we want to find the limit of when x approaches to 2. Right? This means x approaches to 2 from the left, x approaches to 2 from the right. We have to consider both cases. Let's see if we can simplify. If we can simplify, get rid of the denominator, we're lucky. So 2, of course, is not in the domain of this function, right? This original function. So 2 minus 2 in the denominator costs 0. Costs 0. So let's try to simplify. Right? So we simplify, we change 2 to be 2x over x. Right? 2x over x is still 2. Now we can combine the numerator. So the numerator, combine them. Now simplify to be negative x plus 2 divided by x. Then divided by x minus 2 again. Well, dividing by x minus 2 is the same as multiply its inverse, 1 over x minus 2. Well, let's observe this. What's the relation about x over x minus 2 and 2 minus x? They're additive inverse. So we can factor out negative sign from here. You will factor out negative 1. So to get x minus 2. X minus 2 cancel out. So we have a negative 1 over x. Now 2 is in the domain of this simplified version of the function, original function. What do? We just plug in, right? 2 is in this domain. It doesn't cause 0 in the denominator anymore. We plug in, we get negative half. Let's see this example. Can we simplify it? Right? If we can simplify the numerator, right? So 2x, x squared minus 2x minus 8, we can write as x minus 4 times x plus 2. 2 factors, right? So x minus 4, x plus 2. Then the denominator will also has x minus 4. So treating this as just one factor in the numerator, in the denominator. Numerator have x minus 4, denominator will have x minus 4. So they simplified. So now this function simplified to be just x plus 2, a linear function. And of course, we still take a limit to the function. The rational function is simplified. And now, after simplification, it becomes a linear function. And the 4 is in the domain of this simplified version of the function. 4 is not in the domain of the original function because 4 minus 4 causes 0 in the denominator. But now it is after simplification. So 4 plus 2, that's just equal to 6. This is equal to 6. But when we draw the graph would be x plus 2 graph, but with a hole when x equals to 4. Okay, similarly to the previous example. Let's see this example. We also want to factor. The rational functions, we always try to factor first. So let's factor the numerator. So let's group them 2 by 2. I have 4 terms in the numerator. I have x cubed plus 4x squared minus x minus 4. I want to group them 2 by 2. So look at x cubed plus 4x squared. Well, they have a common factor of x squared. So I factor out x squared, I have x plus 4, right? So I made it into 2 factors. Then minus x minus 4, I want to write together as a minus of x plus 4. So my numerator changed to be like this, to have two, to be like this, right? Now I see I can keep going. I see x minus 4, x plus 4, x plus 4, right? I can factor out. Factor out x plus 4. Then the first term left with x squared, the second term with x squared minus 1. Then x squared minus 1 is a difference of two squares. So I can keep factoring. X plus 4, x plus 1, and x minus 1. Right? Difference of two squares. But now, okay, so I finished factoring the numerator. So the numerator from the original 4 terms now becomes having 3 factors. So it's written into 3 factors. Now let's observe the denominator. The denominator I can factor out as x plus 4 and x plus 1. Now I'm looking for common factors in the numerator and in the denominator. The cancel out to be 1, and those two cancel out to be 1. So the function was simplified to be x minus 1, a linear function again. And of course, we still have this limit. We still write down this limit of x approaches -4. But -4 is not in the domain of the beginning function, original function. Right? If we plug in -4, oh, actually, let's see. Yes, it's not, right? Because -4 squared is positive 16. Positive 16 plus this 4, that's positive 20. And -4 times 5, -20. So that would be 0. But after simplification, the function becomes a linear function. Now -4 is in the domain of x minus 1. -4 minus 1, that's just -5. It's just -5. Let's see this one. We also want to simplify, right? So dividing by x, we can do this. We can use this one. Dividing by x is the same as multiplying by 1 over x. So multiplying by 1 over x. Then we see we have 1 over x times x plus 2, which is x squared plus 2x. Then this becomes 1 over 2x, right? It is multiply 1 over x into them. So limit when x approaches 0 of the function 1 over x squared plus 2x minus 1 over 2x. We see we won't be able to just do algebraic calculation from right here, right? Because 0 is not in the domain of the first term, not in the domain of the second term. So what do? We may think about the graphs, right? We may think about the graphs. Let's think about the first one. The first one, the graph x1 over x squared plus 2x, something like this. If you use one of the graphing, so at x equals -2, you have this. At x equals 0, also 0 x equal 2. So, just in any case, I won't be able to use my hand to draw here. So you see that goes to infinity on the left-hand side. So left-hand side limit and the right-hand side limit does not agree with each other. So you can use decimals to graph this, all right? So the left-hand side and the right-hand side. So one goes to positive infinity, one goes to negative infinity, or both goes to positive infinity. So basically, the limit is not a finite number. So what do we see? We see the limit does not exist, all right, for this case. Well, let's see this one. difference of two squares again. So we think x as a square root of x squared. And then 9 is a 3 squared. So difference of two squares. So that can be factored as the square root of x minus 3 and the square root of x plus 3. Right? Square root of x minus 3 and the square root of x plus 3. Then we have a common factor with the denominators. So this is the denominator, this is the numerator that cancel out. So we're left with the square root of x plus 3. So the function was simplified. So 9 is not in the domain of this original function, because square root of 9 is 3, 3 minus 3 is 0, cause 0 in the denominator. But after simplification, now the limit, now 9 is in the domain of this simplified version. So square root of 9 is 3, 3 plus 3, that's a 6. Okay, so those are more exercise. Maybe you can try on your own. Right. 12. Then the answers here, you can check your answers with those.